Chapter 9 is about gravity. Now, gravity is something that men have been studying for a really long time. In fact, if you've spent any time with babies or toddlers, you'll notice that they can spend a long time dropping things off that chair of the high tray or dropping things over the rail of their crib, looking and discovering how gravity works. For a long time, say way back to Aristotle's time, all the way until Newton's time, everybody agreed or seemed to understand that natural motion in the heavens was circular, that things would move in perfect circles. And the natural motion here on Earth was down. If you dropped something, it would fall straight down. Isaac Newton was the first person to come up with the idea that the circular motion in the heavens and the falling of objects straight down here on Earth could be caused by the same force. In particular, the force that causes the moon to orbit the Earth is the exact same force that allows an apple to fall straight to the ground. He came up with this relationship. He said that the gravitational force should be directly proportional to the two masses, that there would be two masses involved, mass 1 and mass 2, and inversely proportional to the distance squared. Most of the time when we're studying gravity, one of the masses is the Earth, and the other is some mass that's falling towards the Earth. But it can be any two masses anywhere in the universe. Now, how can it be? We're going to study this a little more in the next chapter when we talk about satellites. But how can I say that the moon is being pulled towards the Earth with the same force that pulls an apple towards the Earth? It seems like if that's the case, if gravity is responsible for both, that the moon should fall and crash into the Earth. Well, it doesn't because it has a large tangential speed. Now we haven't talked about, we skipped over chapter 8, which talked a lot about circular motion. So I'm going to take just a little time to talk about circular motion. When something moves in a circle, and we're going to just look at the case where we move in a circle with a constant speed. That's called uniform circular motion. So if something's moving in a circle at a constant speed, we know that the speed isn't changing. At this point, if it's moving this direction, its speed would be that way. When it's here, its speed would be this way, or its velocity. Really, speed doesn't have direction. Speeds are velocity vectors. When it's right here, now the one thing we notice, even though the speed is constant, it's not speeding up or slowing down, it's continuously changing direction. And in order to continuously change direction, there has to be an acceleration. There has to be a force because the velocity is changing. And so we have to think about, well, what's the direction of this acceleration? Well, use your imagination because I don't have a demonstration. I have a toy on the end of the string. If I swing the toy around and around on the end of this string, if the string breaks, the toy will go flying out in a straight line. Why is that? Well, the string was providing the force that kept pulling it in towards the circle. Well, with planets, it's gravity that provides the force. So what's happening is, even though the speed is changing direction, there's a force towards the center. Anytime you have something moving in a circle, there has to be a force towards the center. A force towards the center is called a centripetal force. Centripetal literally means center seeking. So we have a centripetal force. That centripetal force could be provided by a string if we're talking about a toy, but if we're talking about the moon orbiting, the centripetal force is provided by gravity. All right, so let's think about a little bit of how this works. So the object's moving so fast. The moon is moving so fast in a circle around the Earth that by the time it's traveled 1,000 meters, it has fallen closer to the Earth. But remember, the Earth is curved, so the Earth curves away. It's its tangential speed that makes it never get any closer, right? If you think about it, if it travels like this and it drops this much, that's the Earth, the moon falling towards the Earth. Well, the surface of the Earth does something like this. And so even though it's dropping, the moon isn't really any closer here than it was here. Well, it is because I didn't draw that very well. It's the same distance away. We'll talk more about that later, but I just kind of wanted to touch on that. So Newton came up with this idea that the moon and everything that orbits in the solar system is governed by the same exact laws of physics and laws of gravity that things like falling apples and baseballs and footballs are governed by. All right, so he came up with this relationship that force is directly proportional to the masses, inversely proportional to the distance squared. What does that mean? Notice it's not an equal sign. We haven't made an equation. Well, one of the things it means is if you double one force, one mass, if we double a mass, it's going to double the force. Think about it. If I come in and I double this first one, so now I have 2 mass 1 times mass 2 over the distance squared, it's pretty obvious that this is going to be double the amount of force. So doubling one of the masses doubles the force. What happens if we double both masses? Well, let's double this one. If I have 2 mass 1s and 2 mass 2s, I've just made it twice as heavy. Well, I can multiply 2 times 2. And I see now my force is 4 times the original force. If we double one mass, it doubles the force. If we double both masses, we're going to get 4 times the force. If I triple both masses, make that one 3 times bigger and this one 3 times bigger, I see that I get 9 times the force. So, the strength of the gravitational force is directly proportional to the product of the masses. The other thing that you're going to notice is it's inversely proportional to the distance between. So let's go ahead and look at this inverse squared relationship. For right now, let's not change the masses, but what would happen if we change the distance? It's obvious as the distance gets larger, this force is going to get smaller. If the distance were to get smaller, that would cause this force to suddenly get larger. Let's play around with how changing distance affects force. Let's double the distance between the 2 objects. So we didn't change mass 1. We're not going to change mass 2. But instead of having a distance d, I'm going to make that distance 2d. I'm going to double that distance. Okay, this requires you to remember what it means to square something. 2d squared means 2d times 2d. That is going to equal 4d squared. You'll notice that by doubling the distance, this force here, we're dividing by 4, is exactly 1/4 the original force. If I decided I wanted to triple this distance, 3d times 3d is 9d squared. The force would fall to 1/9 the original force. If I made the distance between them 5 times 5, that's 25, I'd end up with 1/25 of the original force. So when we think about this law of universal gravity, we are directly proportional to the masses, but we are inversely proportional to the square of the distance. Now, if we want to take this relationship and change it from a proportionality relationship to an equation, we have to add our constant of proportionality. And our constant of proportionality is a capital G. So our force of gravity is equal to capital G, that's our universal gravitational constant, times mass 1 times mass 2 over the distance squared. What's our value? Capital G is 6.67 times 10 to the negative 11. And then it's got some pretty tricky units. It's Newton meter squared per kilogram squared. This is the units necessary so that when you plug it all in, the answer comes out in newtons, because we want to measure all of our forces in newtons. You'll notice this is 10 to the negative 11. It's a really, really small number. What does that tell us? It tells us that the gravitational force between most masses is really small, much smaller than electromagnetic forces. Unless one of these two masses is really large, or possibly both of them are really large, gravitational forces are small. There's a gravitational force between this marker and this marker, but it's so small we can't see it. The only way to get gravitational forces large enough that they're obvious is if one of these things is as massive as a planet. Well, we're standing on planet Earth. The only gravitational forces that are noticeable are the gravitational forces towards planet Earth. Okay? Now, if you look up in the solar system, you'll notice that there's really large gravitational forces between the planets and the sun, or between the moon and the Earth. Again, these are really large bodies, really massive. Everyday objects, the number is just too small. We've got this tiny gravitational constant. And the fact that the gravitational constant is so small is one of the reasons it was so difficult to measure. Isaac Newton did not know this number. When he died, he understood the proportionality part, but he did not have the value of G. He didn't know that gravitational constant. Henry Cavendish is famous for doing something known as the Cavendish experiment, and he is the person that measured the value of the gravitational constant. He found out what G is, and when he did that, he was given credit for weighing the Earth. That's a pretty big accomplishment, but it wasn't hard to do once you calculate the value of G. We know that a 1 kilogram mass weighs 9.8 newtons. We usually say it weighs 10 newtons, but we're going to be a little more precise. Henry Cavendish knew that too. They could weigh things. They knew how much the acceleration due to gravity was near the surface of the Earth. Once he calculated the value of g, he could figure out how big the mass of the Earth is. Somebody before him had already calculated the fact that the radius of the Earth was 6.4 times 10 to the 6th meters. So let's just look at how he did this. He said, well, the gravitational force, here's the formula. Oops, I left out the g. The g is really important. And he said, I know everything except for one of the masses. I know if I have a 1 kilogram mass, it weighs, or the gravitational force is 9.8. I know g is 6.67 times 10 to the negative 11. I'm using a 1 kilogram mass. And the other mass is the mass of the Earth. And I put in the distance. Okay, why is the distance equal to the radius of the Earth? Well, think about it. Here's the Earth. From here to here, that's 1 Earth radius. So if you're at the surface of the Earth, the distance between your centers, which is the distance that you always use the distance between the center of the two objects, is 1 Earth radius. Here's the center of the 1 kilogram object. Here's the center of the Earth. So he knew everything but this number. It's just algebra to do the rest. And he did the algebra. And we find out that the mass of the Earth, I don't know if you can see this down here, but I'm right. Can you see that? Oh, you can. Is about 6 times 10 to the 24 kilograms. It was an easy calculation after he did his experiment and after he had managed to calculate the value of g. Okay. It's not my good eraser. Let me try my good eraser. I hope you guys have been watching the news recently. This is a Tuesday. It was just on Saturday that we launched the SpaceX missile, and the Dragon crew with 2 astronauts up to the ISS. I'm sure you've seen videos of astronauts inside the International Space Station. It looks like they're weightless. There's a lot of people who think that there's no gravity in the International Space Station, and nothing could be further from the truth. If we were to draw a picture of things, and here's the Earth, here's the little International Space Station, here's the moon. That's not drawn to scale. The International Space Station's only about 200 miles above Earth's surface. It's what they call a low Earth orbit. It moves in a satellite motion just like the moon because of Earth's gravity. In fact, here, the acceleration due to gravity is about 9.8 meters per second squared. If you're on the space shuttle, it's about 9.0 meters per second squared. It's smaller, but they're definitely in the pull of Earth's gravity. If they lost that, they'd just be like the toy on the string, and they'd go flying off in a straight direction. Well, the last thing they want to do, they're orbiting in a circle like this. They do not want to suddenly have gravity turn off and go flying off in a straight line. So they definitely have gravity. In fact, the gravity on the International Space Station is almost as strong as the gravity here on Earth. So why does everything look weightless? They have what we call apparent weightlessness. Remember, anything in orbit is in free fall. They're falling towards the Earth, but they're traveling so fast in a circle that they never get any closer. If you can picture yourself being on a very, very tall building in an elevator, if the elevator cable suddenly snapped, you and everything would be in free fall, and you would appear to be weightless because you don't have anything you can push off against when you're weightless. That's called apparent weightlessness. Really important. I want you to understand that things in the International Space Station appear weightless because the space station and everything inside the space station is in free fall. However, they're in free fall because they are still under the pull of Earth's gravity. And the acceleration due to gravity at that particular height is about 9 meters per second squared instead of the full 10. We're going to look at one other kind of problem that relates to that. Let's suppose that you are in an elevator. There's the elevator cable. And you're standing on a bathroom scale. There you are. You are standing on a bathroom scale. Now, if the elevator is at rest, you're at rest, the net force acting on you is going to be 0. So for an elevator at rest, gravity is pulling you down. This is your weight. This is mg. And the scale is pushing back. I'm going to just call that F scale. That's your support force or your normal force. If you're at rest, you're not accelerating. Remember Newton's first law? Anything at rest, the net force is 0. So that tells you that the scale reading is your true weight. If you read your scale right now, the force of the scale is going to equal your weight. It's going to read mg. Well, what if you're in that elevator and you're moving upward at a constant speed? Well, if you're traveling in a straight line at a constant speed, according to Newton's first law, the net force is still 0. So if you're traveling up at a constant speed, that scale will still read your true weight, how hard gravity is pulling on you. If you're moving down at a constant speed, it still reads your true weight. Anytime the net force is 0, these two forces are equal, it'll read your true weight. So, elevator could be at rest, or it can be moving at a constant speed up or down, and it's going to read your true weight. But what if it's not moving at a constant speed? What if it's accelerating up? If the elevator is accelerating upward, then you're accelerating upward because you're in the elevator. What does that mean? What's the scale going to read if you're accelerating upward? Well, your weight doesn't change, but if you're accelerating upward, the net force on you must be upward. This must be larger. If you're accelerating upward, the scale is going to read more than your true weight. So if you stood on the scale and you weighed 120 pounds when the elevator was at rest, when it starts accelerating upward, it may say you weigh 135 pounds. Now, you can accelerate upward two ways. If you're on the ground floor, when it starts moving, it's going to accelerate upward for a while till it reaches a constant speed. The other time it accelerates upward, let's suppose you're coming down and you're getting ready to stop. Well, if you're moving downward and you need to stop, then you need to accelerate upward to slow your speed. So regardless of whether you're accelerating upward because you're on your way up, or whether you accelerate upward because you're on your way down coming to a stop, anytime you accelerate upward, the scale has to push up on you harder than gravity is pushing down. Now, if we accelerate downward, that's going to happen when you're at the very top and it starts moving down. If you start from the top and you're at rest, when it starts from rest and moves down, you're going to accelerate downward. Well, when you accelerate downward, again, your weight can't really change. But while you're accelerating downward, the scale is going to press less on you. You can even close your eyes and imagine that. It's like the floor is dropping out from underneath you. And you will look down at the scale, and the scale will now read a reading less than your true weight. The scale is giving you your apparent weight. When it's accelerating upward, you appear to weigh more than you truly weigh. When it's accelerating downward, you appear to weigh less than you truly weigh. If the elevator cable snaps, you'll be in free fall. When you're in free fall, what's going on? Well, think about it. This completely disappears when you're in free fall. If you're in free fall, the scale will read 0 because there won't be an upward force. When you're in free fall, if this elevator cable suddenly snaps, the only force acting on you will be gravity. There won't be an upward support force from the scale. The scale will have to read 0. So, just remember, regardless of whether you're in the elevator on Earth or whether you're up in the International Space Station or whether you're even on the moon, you're really not outside of the reach of Earth's gravity. However, your weight can appear very, very different depending on whether or not you're accelerating away from the Earth, accelerating towards the Earth, or whether you're in a state of free fall. When you're in a state of free fall, you will appear to be weightless, and that's the situation for the men and women on the International Space Station. We didn't do every section in this chapter, so just pay attention to the sections that I've written notes about and that we've talked about in this lecture. Thank you.